Sorry for not being able to be with you guys today. Let's take a look at this expected value and variance booklet here for the random variables that are going on. Last day we briefly took a quick look at this, and we're talking about the idea of expected value, which is also called a central tendency. The idea being, if you have a target, imagine the center of the scattering of shots as a good idea of where the next shot will be. So with these four things, you could say, well, the middle is around there. For this one, maybe the middle around here. For this one, the middle around here, and this one, the middle around here. Okay, so this idea of expected value is calculated by this formula, the sum of every option multiplied by its probability. So here, if you've got a distribution, it's the option times its probability plus the option times its probability. So you can see you would have this kind of a pattern going on. That's how this formula works. We saw at the end of last day also that if you have a uniform distribution, which means that the probabilities for all options are equal to each other, then this is just called the arithmetic average, or the average that you're typically used to, just adding up all the values and dividing by how many there are. When the probabilities are not always equal, then this is called a weighted average. Okay, so the expected value is the weighted average. If it's the uniform distribution, then it just simplifies to the arithmetic average. So let's talk about the expected value of a transformation then. So here, let's say y could be 0, could be 1, or could be 2 with these probabilities. Just a very simple distribution. Here I mean, I usually do horizontal, but this is the same chart, just vertical instead of horizontal. Instead of x's, I've got y's. Okay, so here, every option multiplied by its probability. Okay, so 0 times a quarter, 1 times a half, 2 times a quarter. Then we'll add them all up. So here, the sum of y times by the probability of its particular y. 0 times a quarter plus 1 times a half plus 2 times a quarter is, of course, 1. So I would expect y to be 1. What about the expected value of this kind of crazy looking function? Okay, so here I could make a new category here. So y divided by 3 subtract 4. Here y is 0. So 0 divided by 3 subtract 4 is negative 4. Here, y, which is 1, divided by 3, subtract 4. That's negative 11 over 3. Here, y is 2. 2 divided by 3, subtract 4. This is negative 10 over 3. So now I just have a new listing of values. Instead of the value 0, 1, 2, I've got negative 4, negative 11 thirds, and negative 10 thirds. But it's not any different. I just have options and I have probabilities. So the expected value of this complicated mess is just going to be this option multiply by its probability, plus this option, multiply its probability. So here you can see I've got some negatives, which of course are going to come into play. Negative 4 times a quarter plus negative 11 out of 3 times a half plus negative 10 out of 3 times a quarter. I add that up and I get the expected value of negative 11 out of 3. Okay, so if I wanted to make a probability density graph, then here for just y, and the probabilities, the y's were 0, 1, and 2, then it would look like this. So you can see some things that we've talked about. This has definitely got some symmetry. The other thing to notice is that the expected value is actually the balance point. Where would you put your finger to balance this graph? You would have to put it right here, and then of course it would balance perfectly. So the expected value is like thinking about the balance point, or with targets, the middle, if you will. Okay, so if we go back, we can see how this works with a few different examples. So previously we talked about throwing 3 coins up, and you get to keep any coin that lands on a head. There were two nickels and a dime. Okay, so the probability distribution, you might recall, looks like this. Winning is a little bit different than profit. Remember, it actually cost you 10 cents to play. So we could win some amount of money, but then of course we've got 2 variables going on here, somewhat similar to how we've got 2 variables going on here. Okay, you've got the y's and then you've got some sort of transformation on the y's. Okay, so here you've got the probability of how much money you would win, except for the fact that you had to pay to play. Okay, so here are 2 different variables, 2 different sets of options. If you're talking about how much money do you expect to profit, then of course we'd want to be talking about these options times by their particular probabilities. So here, this is where we lose 10 cents, this is where we lose 5 cents, here's where we gain or lose nothing. and here's where we win 5 cents, and here's where we win 10 cents. Again, you could flip back to see these probabilities and how we got them in an earlier booklet. But when we do the expected value, this option times its probability plus this option times its probability and so forth, then we see here the expected value is 0. So you expect to win 0 money every time you play. I mean, sometimes you win, sometimes you lose, but because it's balanced, it's symmetric, or it's, it may not be symmetric, I suppose. You might want to graph it to see if it's symmetric or not. But seeing as the expected value is 0, we call this fair. We call this a fair game because we could either win or we could lose. If the expected value is 0, I mean, if you were in Vegas, would you play a game with the expected profit being 0? I guess it's up to you, everything's subjective. But if it was an expected value of 0, I would certainly play because what this means is every time I play, I would expect to not win any money. So in the long run, my wins would cancel my losses. If you would you want to play? I mean, this, of course, again, it's up to you, but if you ever had a game that did have an expected profit of 0, I would suggest playing, especially if you know that it has expected value of 0. Because if you play and you lose money, then you know in the long run you will break even. So why not keep playing and eventually, hopefully, get your money back? If you're winning, then I suggest stop playing because the expected value suggests that you will in fact lose money. But the point is that here, if you played a lot of times, the average of your winnings and losings would all cancel out. That is the idea of the expected value. So here we expect to win 0 every time we play. We can apply this to other ideas that we've thought of. So this is similar to an example we talked about last day. Suppose you have got a fair die and you toss it 2 times. Let y be the largest of 2 faces that appear. Here I've got a little typo. I put 3, but that's a little more difficult. We don't want to necessarily get into that. So here, let y be the largest of the two faces that appear. And it takes $10 to play. If you roll the 2 die and get 4 times as many dollars as the largest, would you play? Okay, so I mean, there's lots going on here. Let x be the here I've called it y, but here I called it x. Sorry for that. So maybe just make this an x, or either make this a y. So here, what could I roll? The largest value I could roll is a 1, 2, 3, 4, or 5. Okay, the largest value of a 1, that means there's only one way of doing that. Both times I roll a 1. Largest value being a 2, of course, you can see there are 3 ways, either a 1 and a 2 and a 1, or a 2 and a 2 out of the 36, and so forth. Okay, so I can get the probabilities, except for it costs me $10 to play, so I'm going to subtract everything by 10, but I also get to keep 4 times the largest number that I roll. So here, if x is the largest number I roll, 4 times it is the amount of money I get, but it cost me $10. So 4 times x, subtract 10. So here, if I rolled a snake eyes, the largest number is a 1, I'd get $4, but it took me 10 to play, so I have an overall profit of negative $6. And here, putting this in here, for example, 4 times 4, okay, is going to be $16 minus the 10 it cost me to play. The profit is 6. So then, would I want to play this? Well, each value, in this case the profit, times by its probability, respectively, then add them up. And what I got here is I'd expect a profit every time I play of positive $9.76. So would you want to play this game? And I think the answer is certainly yes. I mean, every time I play, I would expect to win a positive amount of money. This is nice. I think that, yeah, I definitely would want to play that. Okay, so let's talk about some other rules. This works. Expected value works for any linear function. The point is, whatever's in the brackets here, that's what goes. That's the option that gets multiplied by the probability. That's what you need to remember. So here's some examples. Expected value of x we've seen. This is just x times the probability. Expected value of y. This is y times its probability. Expected value of x squared. This is x squared times its probability. Expected value of any function is just the function times its probability. Okay, so I guess the thing that I want to talk about here is, especially here in this case, we're going to see this very soon, expected value of x squared. You want to be squaring the options, not the probabilities. And the other thing that you need to know is the expected value of y squared is not the same thing as just taking the expected value of y and squaring it. So here the square on the inside is different than the square on the outside. So let's just see. The example that we saw earlier was if y was 0, 1, or 2 and the probability that came. Let's also square y. So here's 0 squared, 1 squared, and 2 squared. Okay, here I've obviously got a typo. 2 squared is not 2, it's 4. I've written it correctly over here at least, but this should be a 4. So here the expected value of y is just 0 times by this, 1 times by that, and 2 times by this. Add them up, and we saw this earlier. You got the expected value of y. The expected value of y squared, we don't want to just square 1. 1 squared is 1. What we want to do is square the y value. So here I've got the y value squared. This should be, of course, 4. Then this is going to be 1 squared, which is 1, times by a half. This will be 2 squared, which is 4, times by 1/4. So 1 times a half plus 4 times a quarter is actually 1.5. You can see the point that I'm trying to make here is that the expected value of x, if I squared that here, so the expected value of y, if I squared that, it would be 1 squared, which should simply be 1, is not the same thing as the expected value of y squared, which happens to be 1.5. Okay, let's talk about some other rules so that we can get things going simpler. What is the expected value of a constant? Okay, so here the question is, if something is a variable, it's allowed to vary. So what do we expect it to be? This is a question. But if something is a number, then what do we expect that number to be? So what do you expect a number to be? For example, what do you expect the number 3 to be? Well, I expect a 3 to be a 3. I expect a 17 to be a 17. I expect a pi to be a pi. Okay, the expected value of constants are just the constant. There is no variation because they are not variables. They are constant. That's why they're called that. Okay, so the expected value of any number is just that number. So then something that's nice is if you've got a constant multiplied by a function, you can just take that constant outside the bracket, so to speak. For example, what I mean is the expected value of 5 times x. Here you could write it this way, and you could list them out. Here's how the pattern to list it out, but you could see they all have a common 5, and you can just take that 5 outside the brackets. At the end of the day, the expected value of 5x is just 5 times the expected value of x. When you have a constant, you can just take it outside the expected value sign. Okay, what about something like this here? The expected value of x plus 2x subtract 3x squared. Okay, so here, if I like to think about this like it's algebra, and I'm going to distribute the expected value inside the brackets. That kind of makes sense to me. So this is going to be the expected value of x, and then I can separate it with this thing, plus the expected value of 2x, subtract the expected value of 3x squared, which of course I could further simplify. This is the expected value of x, plus here I could bring the 2 out, plus 2 times the expected value of x. Subtract 3 times the expected value of x squared. Here I would have 3 expected values of x. I could actually say this is equal to 3 expected value of x. Subtract 3 times the expected value of x squared. You could simplify it from there. This would be 3 times the expected value of x, subtract the expected value of x squared if you wanted. But I just wanted to show you that you can bring the expected value in. So if we were using this rule in conjunction with this rule, we could really simplify this a lot. So previously we showed, here let me just zoom up quickly. We showed that we could solve this question this way by just transforming each of the y's into their respective options. There's another way that we could do this if you find it more handy, which is here we can bring the expected value in. Expected value of y over a third. Subtract the expected value of 4. Here we can rewrite y over a third by 1/3 times a y, the coefficient just being 1 over 3 of y. And then here, what do we expect 4 to be? 4 is a constant. I expect a 4 to be a 4. Here, I can bring the 1/3 out. It is a constant. What do I expect 1/3 to be? I expect it to be 1/3. So here, then, the expected value of y divided by 3 subtract 4 can be calculated by just saying this is 1/3 times by the expected value of y subtract 4. What was the expected value of y? Well, let's just quickly go back. the expected value of y, okay, so when I just did the expected value of y, we saw the expected value of y was 1. There it is. Okay, so anywhere we see the expected value of y, oops, sorry, I'm going too quickly here. The expected value of y is 1. So 1/3 times 1 subtract 4. And you can see this is another way of calculating the expected value of y over 3 subtract 4. Same answer that we got, doing it sort of the longer way. So this can really speed you up knowing these rules. Okay, so trying to put this all together, what's the expected value of this complicated mess? Well, again, I'm going to bring the expected value in. So this is going to be here, the coefficient with y squared is 1 over -9, so that's a constant, I'll bring it out. Then this is the expected value of the variable y squared. Here plus 4 is the constant with y, so it'll be plus 4 times the expected value of y, and then here subtract expected value of 6, which of course is just 6. So here then, this can just be quickly calculated as 1 over -9 times the expected value of y squared plus 4 times the expected value of y, subtract 6. Again, what was the expected value of y squared? You might want to quickly zoom up, remind ourselves the expected value of y squared. Where did I calculate that? I calculated it somewhere. Right here. The expected value of y squared is 1.5. The expected value of y, as we saw earlier, is just 1. So we can just put those values in to here and there. Okay, so there are some good examples on the lab. If you're having a hard time with this, make sure to go to the lab videos that I've prepared and you can really get a better example of what's going on here. Well, what about variance? So variance, what is the definition of variance? It's a little bit complicated, but every value, how far away is it from what is expected to be? Then we square that. So here, this is the definition of something called variance. And it's a little bit confusing, but that I'll show you how it works here. So here, the variance, so V for variance, there's also these symbols if you like. The variance of y is the expected value. So if here I've got a y, just anywhere there's an x, I'll sub out the x and put in a y. This will be the expected value of y subtract mu squared. Okay, so what's going on here? Well, this is just the expected value of y subtract, what is mu? Another symbol for mu is the expected value. So y subtract the expected value of y all squared. So here, remember, we found the expected value of y to be 1. So here, what is y? It's 0. What is the expected value of y? It's 1. So 0 subtract 1, which is -1, squared, which is +1. Y, which in this case is 1, subtract the expected value of y, which is 1. So 1 subtract 1 is 0, squared is 0. Here the value is 2, subtract the expected value of y. We've seen a number of times the expected value of y is 1, squared is equal to 1. Okay, so then if I take these values and multiply them by their respective probabilities, 1 times 1/4, 0 times 1/2, 1 times 1/4, I will get half. But here the thing that you need to know about variance is it's in units squared, because I've squared the units here. Okay, so this is half a unit squared. The standard deviation is called the variance, the square root of the variance. So the standard deviation is if I take here the variance and I take the square root of it. So the root of a half is approximately 0.707. So the standard deviation of y is plus or minus, because you could have a positive or a negative root, 0.707 units. Okay, now that was probably pretty confusing for you. Of course, there's a little bit easier way to think about it. Well, I mean, I don't know. Easy is a frame of mind. I don't know which way you like, but here's a different way of thinking about it. Okay, the expected value of x, we saw the definition above. If we just write out literally what squared means, it means this times itself. Okay, here let's just use FOIL to actually expand this, which of course gives us this. Okay, then I'll bring the expected value in. So this is going to be expected value of x squared. Here, -2 and mu are constants, so this is going to be -2 times mu times the expected value of x. and then bring the expected value into here. Well, here again, mu is a constant, so the expected value of a constant is the constant. Then there's a little bit more I can do. I can notice that the expected value of x, another name for the expected value of x, as you could say here, is mu. Okay, so this I could just replace with mu, which gives me 2 mu squared. Okay, so I've got this. Then what I can do here is I've got negative 2 mu's, and I've got a positive mu squared. So here's a negative 2 mu squared, and here's a positive mu squared. Together, I've got just 1 negative mu squared, so I'm just combining these two. There it is. And then here, again, the other name for mu, again, as you remember, is expected value of x. So then here, I can rewrite the variance. Another definition of the variance of x is expected value of x squared subtract the expected value of x all squared. So this is called the second moment. So the expected value of x squared, that's called the second moment because there's a 2 here. The expected value of x is called the first moment. So this is the second moment minus the first moment squared. Okay, so I mean, that might not mean a whole lot to you. Again, that might have gone a little bit over your head, but the point is that you can use this definition of variance if you like. Okay, so the point is if you want the variance, you can find the expected value of x squared, subtract the expected value of x all squared. Remember, what was the expected value of y squared? Back to our example, every option, square it times by its probability. So 0 was the option squared times by the probability of 0, plus 1 squared times the probability of 1, plus 2 squared times the probability of 2. That gives us the expected value of y squared, or the second moment. Again, we already saw how to get the first moment. This is just every option, don't have to square it because there's no square here, 0 times a fourth, plus 1 times a half, plus 2 times a quarter. That, of course, is the expected value of y. This is the first moment. This is the second moment. The variance is the second moment minus the first moment squared. So 1.5 minus 1 squared, which here is a half. Okay, so two things you should know about the variance is, first of all, variance can never be negative. Variance will always be positive. So here the second moment subtract the first moment squared will always be non-negative, always, always, always. And the second thing is that you can either write the variance this way, the expected value of, or the second moment minus the first moment squared, that's one way, or you can write it this way, the expected value of x subtract the expected value of x squared. There are two definitions for the variance. Okay, so what about some other rules? Okay, so show that x, which equals 1, y plus 1, and y have the same variance. Now this might be a little confusing to you. What's actually going on here? You'll remember from your pure math class that when you take a function, you just add 1 to it. All you're doing is just shifting it. You're just shifting it up 1. It's the same, like if you add x, if you graph the function x, and then you graph the function x plus 1, you get the same picture, just one picture is shifted up 1 unit. So if you have the variance of y and the variance of y plus 1, all you're doing is shifting the same picture. The question is the spread the same? Well, think of a shape. So here's a shape, for example. Here's a square, and I happen to put the square right at the point of the origin. But if I shifted that square over 1, or up 1, or to the right 1, or if I shifted it any which way, would that change how spread out it is? Would that change how this is allowed to vary? It's allowed to be anywhere in this box. If I just shift this box over, does that change it? And the answer is no. So let's show that. This is definitely tough. Okay, so this is harder than anything you would see on a test or anything. But I wanted to show you that we could use the tools that I've just told you about to actually show this is true. So let's let mu equal expected value of y, and the variance to equal the variance of y, which of course can be written this way. Okay, so the expected value of x, which here another name for x is y plus 1. Just sub in anywhere there's an x to sub in y plus 1. That's going to, of course, by using the distributive property of the expected value, just be the expected value of y plus 1. The expected value of y can be called mu So this is going to be mu plus 1. So here the expected value of x is this. The variance of x is going to be the expected value of x subtract x, the expected value of x all squared. That's one way of saying it. That's the way I'm going to use here. So let's actually sub in the expected value of x. We just saw that the expected value of x is called mu plus 1. So here let's just sub in mu plus 1. And we get x subtract mu plus 1 squared. Okay, fine. So here then let's cancel, or let's sub in what x is. Okay, the actual name of x is y plus 1. So we throw that in there, and we can cancel off the 1s. We get y subtract mu squared, which of course, this is the definition of variance. So what we've seen here is the variance of x is equal to the variance of y. Again, that's not really the point of what I'm trying to say. What I'm really trying to say is the variance of any sort of shift is still the variance of the variable. Okay, so let's see another interesting point. If you have the variance, how do you bring this variance into the bracket, so to speak? When it was expected value, it worked just fine. And here, the coefficient that's with any variable, what you do to get them outside of this bracket, so to speak, is you square them. Okay, so the variance of a times x plus b will just end up being a squared times the variance of v. Okay, so again, let's see this. Let's see this in action. Let's see why that's true. This is true. Let's see why it's true. We have to prove it. Okay, so let y, and there is a video for this as well that you can check out in D2L. So y is a times x plus b. We'll sub that in here. Well, the variance of y, of course, can be defined this way. Okay, so then here, y squared, well, here's y, so let's just put in y. So y squared is that, and here this is the expected value of y, and then squares on the outside. Well, okay, so here we'll just replace y with what y is actually called. Here we'll expand this out. Okay, so here this is all expanded. Okay, and then we'll bring in the expected value as we were taught to do a few steps ago. Not a problem. Then here the expected value, let's just bring it inside. Okay, this is a times expected value of x plus b. Now we have to square this. Okay, so all I've done is just expanded this out here like this. Okay, so now the really neat thing is you get a ton of cancellation going on here. So this is going to cancel this, and this is going to cancel this, and all I'm left with at the end of the day is a squared times the expected value of x squared, subtract a squared times the expected value of x with a square on the outside, which of course, if you just collect the common a squared, you're going to get a squared times the expected value of x squared, subtract the expected value of x all squared, which is, of course, the definition. This is, of course, the definition of the variance. So this is a proof. Okay, so I've shown mathematically that this is true. Again, you're probably not worried about all of that. All you're caring about is when I want the variance of a formula, of an expression, any constant that is with the variable can be just squared when you take it out. That's all you really need to know. But I've shown that it's true. Okay, so here, let's recall, when we've got this going on here, we've seen the expected value of y squared, we've seen the expected value of y. Okay, so here the variance is just the second moment minus the first moment squared. So this is going to be 1.5 minus 1 squared. If we wanted the variance of y over 3 subtract 4, then all we need to do, according to that proof up there, which is true, here the coefficient that is with y, to bring it outside of this variance bracket, we will square it. So this will be 1 over 3 squared. Then we bring in the variance. This is going to be the variance of y, subtract the variance of 4. Well, how much does 4 vary? The answer is none at all. 4 does not vary. So here, this just goes away. So here, then all we're left with, because this constant goes away, constants don't vary, But what we're left with is here 1 over 3 squared, which is 1 over 9, times the variance of y. We just found the variance of y to be a half, so this is 1 over 9 times by a half, so this is 1/18. Again, there are some really good examples on the lab that you've already gone through. Check out the videos over and over again if you're having a hard time seeing how this works. Also, then there are some examples at the end of this booklet. There are, in fact, videos. Every single one of them, there's a video on D2L. If you're having a hard time, check it out there as well.